If you've ever been watching the news during a major storm event, you may have noticed that over time, as storms travel, they rotate in a certain direction. If you look at storms in the northern hemisphere, you see that they rotate counterclockwise, whereas you look at storms in the southern hemisphere, they rotate clockwise. The reason this happens is known as the Coriolis effect. The Coriolis effect causes fluids to curve as they travel across Earth's surface. And the reason that they curve in different ways in different hemispheres is due to the rotation of the Earth. To better understand this, let's look at some examples. As we know, the Earth rotates from west to east, and we also know that the Earth is spherical, so it's going to have a much higher radius around the equator than it does around the south or north pole. What this means in the long run is that there's going to be a much greater angular momentum around the equator than there is at either pole. We can really start to see the Coriolis effect come into play on large scales. Let's have a look at a plane starting at the equator and going north. And you can see that from the view of the plane, it's going in a straight line while the Earth rotates below it. If we were to look at this from the reference point of the Earth is going to be stationary while the plane is still moving overhead. But the plane is going to appear to divert to the east, regardless of whether it's going north or south. This is because the angular momentum of the plane is conserved as it travels to areas with a smaller radius. In the past two examples, we saw two separate trajectories for the plane. Now this is because the plane itself is in an inertial reference frame, which means it's not accelerating. While when looking at it from the point of view of the Earth, we're in a rotating reference frame or a non-inertial reference frame. The key consequence of inertial reference frames is the introduction of inertial forces. Inertial forces are basically corrections to Newton's laws of motions. The two that we see appear here in rotating bodies are the Coriolis force and the centrifugal force. As we saw in our earlier examples, the Coriolis force is an inertial force that acts on objects that are in motion relative to a rotating frame of reference. Now that we understand how this force acts, we can derive its equations of motion.
The motion in an inertial frame is related to the motion in a rotating frame by the equation. In this equation, the prime values are what is observed in the rotating frame. From this, we find the Coriolis acceleration. Suppose we want to relate the Coriolis acceleration to our reference frame here on Earth. We first need to define our basis vectors. We set the x direction to be east, the y direction to be north, and the z direction to be directly up. Phi gives us our angle relative to the equator. If we now solve for the Coriolis acceleration relative to our frame on Earth, we find the following relation. This equation can be used to demonstrate the effects previously discussed. Suppose we are examining the effects of vertical motion along the equator. Our equation reduces to the following. From this we can see that as we move away from our axis of rotation, we begin to accelerate against our rotation. The opposite is true if we move towards the axis, exactly what we expect for conservation of angular momentum. Now suppose there is no vertical motion. That is, the velocity and acceleration in the z direction are zero. The Coriolis acceleration now reduces to the following. This equation shows that objects in the northern hemisphere deflect to the right, while objects in the southern hemisphere deflect to the left. Also, these deflections become stronger the closer to the poles you are. This is what you would expect, since motion near the poles has a greater effect on your distance from the axis of rotation.
Now that we have a better understanding of the Coriolis effect, we can see why storms in the northern hemisphere spin counterclockwise, while storms in the southern hemisphere spin clockwise. I hope this helped your understanding. Thank you for watching.
Created using Powtoon.